Hi everyone, welcome to our free Mathcounts training, week number 2. So, this week we have 4 sets of minis. We are still focusing on primarily on word problems, and the speed is a big topic in many word problems, and we will work on quite some speed-related problems. So at this stage, we'll focus on using algebraic methods to solve word problems because now at math count level, we are kind of beyond the stage when we use arithmetical method to solve word problems. So now with algebra available, which is super powerful, we should be able to easily solve all kinds of word problems. But some problems do need special attention. So let's talk about key to solving rate or speed related word problems. In the typical speed related word problems, you need to keep a fundamental concept really just a you know feel very comfortable and feel very familiar with that concept, that is this relationship when you have three variables: speed, time, and distance. Okay, so the distance you travel would be the product of the speed you traveled at and the time spent on the travel. So this relationship is quite clear. So for example, you travel at 60 miles an hour, you travel for 3 hours, then the distance you traveled would be 180 miles. So this is a multiplication. So we call it a multiplicative relationship. But from this multiplicative relationship, you will also get a two division relationship. So apparently, the speed would be the ratio between distance and time, or just a division, distance divided by the time. And another one, essentially the same, is that time would be the ratio between distance and speed, or you just divide distance by speed. This one is a little bit uh, less obvious if you just look at all the parameters, because speed usually itself is defined. The unit of speed would be something like miles per hour. This would be the typical the unit for the speed. Of course, you can change that to any other metrics like kilometers per minute and so on. So the point is that a quantity like speed itself, its unit usually is kind of compound um, uh, entity that requires you have two basic units. While time, of course, usually just hours, minutes, and so on. And distance is just miles, um, kilos, or any other measurement. So when you think about the division relationship, like distance further divided by a speed quantity, the unit would be something like you have miles divided by miles over hours. So it's this part together with um, the numerator combined with the denominator, but denominator itself conceptually is a fraction that can cause a little bit just kind of conceptual confusion. But the key is to understand it's always this multiplicative relationship among three parameters. That's very important. This is the big picture. And actually, this is not just limited to speed related problem. In general, in our real world, many um, such a multiplicative relationship exists. So if we abstract the same relationship into a mathematical relationship, it's really something like you have three perimeters. Now you have A times B equals to C. And of course, this will also give you two division relationship. A will be equal to C divided by B, and B equals to C divided by A. So, for example, we can have many real life examples. Let's talk about, say, how much money you can earn on a part-time job. So one parameter is your hourly wage, how much money you can earn in a single hour, and how many hours, say, you work in a week. Then you times A and B, you will get your total wage, your total money earned in that week. Okay, so this is apparently A times B equal to C. So another example, let's just say we try to count how many students in your school. So A could be the number of students in every class. Let's just assume that in this school, each class has exactly the same number of students. So A could be that number, and then B could be the total number of classes in your school. Then, of course, the total number of students in your school would be A times B. So this kind of relationship is just so widespread. And in many word problem, the key is to identify the underlying such multiplicative relationship. Okay, so that's the big picture, and it's always to keep a big picture in mind. Don't get too just buried into the specific details of a specific problem. Keep your vision. Okay, now let's talk about our first problem. This is number 6 from mini number 28. So uh, Jack and Jill climb a hill, and after uh, they reach the top, then they come back to home. So they start from the same place, meaning at the destination, maybe at the top of the hill, and then start at the same time, same place, then start going home. But Jill drove 10 miles per hour faster than Jack. So Jill is a speedy driver. So, of course, because they will come back to the same home, so they will travel the same distance because Jill drove faster, so she would just need less time. So she drove only for 80% of the amount of time that Jack drove. Okay. So what was Jack's average speed on his drive home? Okay. So we got quite some statements, but all we need is to understand what each English sentence means and translate such just English statements into mathematical statements. Because we will try to use algebra to solve the problem, um, usually it's a good idea to choose the most convenient variables. So in this case, uh, what would be the best variable? Usually it's just what you are being asked to solve. So you are asked to get the average speed of Jack, and there's no apparent reason why we should not do that. So let's just say Jack's speed would be x. And we have to agree on what is the unit of x. So here, because we already know there's another one, say Jill drove 10 miles per hour faster. So we assume this x means miles per hour for Jack. Okay? So now we can see what we can get. So the first couple of statements did not really give us much data, but we do know they start from the same place, therefore they will drove the same amount of distance. So the first meaningful statement is that Jill drove 10 miles per hour faster than Jack. So we could write down, so the first is speed of Jack. We could use something like that, but this is just really for our analysis. We can use simpler notation like S1 or S2, but this is a little bit more um, just clearer. So Jill's speed would be x plus 10, right? Because she drove 10 miles faster than Jack. So that's the first relationship. Now, the second statement say she drove for 80% of the amount of time that Jack drove. Okay, this is a very important statement, but now this is about the amount of time that was needed by Jill and Jack. So from our formula, the time would be distance over speed. Now we do know the two speed, but we don't know the distance, right? Okay, but do we really need that? Well, you think about this. Whenever you introduce a new variable into your solution or your system of equations, you generally need one more equation. And your number of equations generally need to match the number of variables you have in order to solve them. Okay, so for now, we only have one variable, that is the speed of Jack. But how many equations we have? Well, we don't really have any equations yet because we haven't established any particular relationship. But for now, if we need another variable like the distance, then we will be able to see we essentially need one more equation. So why don't we just choose that variable for now? That just said the distance they will travel is actually d. Okay, so now in that case, this statement should give us a lot of information. So Jill drove for 80% of the amount of time that Jack drove. So now what is the time that Jack need? That would be distance over Jack's speed. That would be x. Okay, so what would be the time that Jill spent? That must be d over x plus 10. So we got the two times quantities. But what this says is that Jill's time is only 80% of Jack's. So that easily can convert this relationship. So this we know this is the amount of time Jack spent times 80% or 0.8 or 4 over 5. Generally, we prefer fractions because 0.8 is easily 5 over 4. That would be the amount of time spent by Jill. So now what you can see is that while we actually only have one equation, but this equation happens to be that we can actually cancel out the distance d, right? So, which is kind of just a surprise and a sweet surprise, because otherwise we won't be able to solve those two variables because that's the only equations we have. If we only have one equation, two variables, in general, we cannot solve the two variables. In this case, we still cannot solve d, but we can solve x because we now have a complete equation that is 4 over 5x equals to 1 over x plus 10. Okay, so this will give you the equation you need in order to solve x. So easily you cross multiply this just ratio equation, and you get 4x plus 40. Okay, from there you can get easily x equals to 40. Okay, so that is a little bit surprising because you really do not have much other just opportunity to solve D because you don't need to solve D. All you need to solve is Jack's speed. So what this means that is that actually the distance does not really matter in this problem. Whether it's 100 miles or 10 miles, this ratio actually is always the same. Okay, so what this means is that the time is 80%, and then the speed, geo speed, must be also 80% of uh, jack. So that is where you go from 40 to 50, and you get 10 miles speed difference. So from this problem, what we really learn is that speed problems usually are not that difficult. You just keep the key relationship, that multiplicative relationship in mind, then you properly translate every English statement into a mathematical statement, and then to see what kind of equations you can get. A, a correctly written problem will always guarantee you that no matter how you do it, you will have the same number of equations as the variables you have because the problem is a legit problem. So um, you should be able eventually solve that. So in this case, don't be afraid of one actual variable. Somehow magic will happen. And in this case, even with one actual variable, you can cancel that out. Okay, so this is a fairly easy problem, but it tells us how to approach a speed related problem. Okay, next problem. Terunesh and Sally start at the same point on a 400-meter circular track. Okay, so we all know what track field is, but it's quite rare to have a circular track, right? Usually it's not fully uh, circular, but uh, let's just assume that's the case. So they start running at the same point, in the same direction around track. This is kind of, if you have worked in that word problem, this is kind of typical setup. So what this means is that you have a circular track, you have two guys, they will start they will start running along the same direction. Whether it's clockwise or counterclockwise doesn't really matter. So they start at same point in the same direction. So Tirunesh runs at a rate of 8 meters per second, while Sally runs at 7 meters per second. How many seconds will pass before the two of them are again at the same point? So you really have to understand what the problem is about. So the two guys travel at the same direction, in the same direction, at the same place. So apparently one is faster, 8 meters per second. The other is slower, but it along the same direction. So immediately after they stop, the fast guy will be ahead of the uh, slower guy. So essentially, when they meet again, it's like once, let's just say the green guy here runs faster. So immediately he or she, I think in this case, I actually don't know the gender of Tirunesh. Sounds like an Indian name, but I'm not sure whether that's a girl's name or a boy's name. But let's just assume uh, this is the green guy here. Okay, so immediately he or she is ahead of the blue person. That's just a person. I know this is Sally, but then the green person essentially is chasing from behind because this is circular. So when they meet again, essentially the green person would have run one full circle more than the blue person, right? You just think about it. When they meet again, because the green person was already ahead, So he's actually catching from behind with one actual circle under his or her belt. So this is really just a like a typical speed problem. So the guy is faster, this guy is slower. So their speeds this difference is really a minus 7. So you have to understand the basic speed problem. When they two person running in the same direction, they have a speed difference, and then over a certain amount of time, their distance difference would be that speed difference times the time. It's very easy to show that. It's essentially the distributive property. So when they travel along the same direction, the distance difference is the time times the speed difference, which makes sense. So in this case, that's exactly what's happening, but the setup is along a circular circle. So the speed difference is just a minus 7 meter per second, I believe. Then the distance difference after they meet again would be one full circle, which is 400 meters, I believe. So it would take this much time for Nash to catch up Sally again. Okay, so this is a very straightforward, very basic word problem, but in a circular track field setup. So this will give us 400 seconds. Okay, um, nothing but just a special setup in the circular track um, field. So this would be 400 seconds because the difference in terms of the speed just 1 meter per second, and this is a 400-meter circular track. Okay, next problem. Similar setup. The only difference now, the same two guys, they instead of running in the same direction, they run in opposite direction. Okay, the speed is still a7. So this time, at the very beginning, Sally would run in this direction. So when they meet again, they give each other a high five each time they meet on the track. So we have to understand what that means when they meet again. Apparently, they will go, 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 go. At some point, the green person came here, and the blue person come here. So when they meet again, really means that they together have run a total combined one full circle. And this is also another very basic speed problem. Let's just say where you have a distance to destination A and B, they run or travel against each other. In this case, what is the relationship? Instead of getting the difference between their speed, we need to get the sum of the two speeds. So speed A plus speed B would be their combined speed. Then this divided by the distance would be the time that will take for they to meet. And that's exactly what happened here. But the setup, rather than a straight line segment, the distance, now it's a full circle. So that means that it would take this much time, 400 over a plus 7, this many seconds for them to meet uh, um, again. The problem is that they will keep doing this, right? So in how many minutes? In 5 minutes. So that means that it takes this much time, which is 400 over 15. We can simplify it a little bit. It would be 80 over 3. And remember, this is seconds. This many seconds for them to meet once. But they will keep doing this in 5 minutes. So how many times they will get a high five, which means that how many times they will meet within the 5 minutes window. So because it takes this much time to meet once, and 5 minutes is just 5 times 60 seconds. That's 300 seconds. Then we have to divide this quantity to see how many times this will get us. But this doesn't mean that this will be exactly an integer number, right? So actually, if we do it, we'll see that this is 300 divided by 80 over 3. So we'll multiply the reciprocal and see that we cancel out the 0 here. So it's really 90 over 8. And this will give us, if we write this down into a mixed uh, uh, number, that would be 11 point, because 88 at 2, so 11.25 or 11 plus 1 uh, a quarter. So this many times, this the unit is how many times they will actually meet again. But because there's no such thing that they meet just 1/4 time, that really means that we have whatever fractions we have here, we have to abandon it. That means that they all after the 11th meet up, they did not have enough time to meet again. So the total times they will have 5. It's just the integer portion of this number, which is 11. So they will high five 11 times. Okay, so this is also a very basic speed problem, but you do need to understand the setup. Okay, next problem. All right, this problem is a little bit more interesting. So a man is running through a train tunnel. So when he's two-fifths of the way through that tunnel, he hears a train behind him that is approaching. But he's in the middle of the tunnel, so he has not reached the train has not yet reached the tunnel of the entrance. So the train speed is at 60 miles per hour. So the man could runs back or runs ahead. But it says that no matter what he chooses, either runs ahead or runs back, he will actually reach the end of the tunnel either way at exactly the same time when the train reaches that end. Now we want to know the speed of the man. What rate in miles per hour is he running? So we have to draw a kind of just a picture to see what is going on. So the man is running through a tunnel, and he's running in this direction. Let's just say could be. So he runs through at 2/5 place. So the man is here at this position. So at this point, because he's running this position, at that time he heard that there's a train coming from behind. So the train, we don't know exactly where the train is, but just let's say there's a train. The locomotive head is right here. So there's some distance between that train and the entrance of the tunnel. Okay, so at this point, the guy will make a decision, either continue to run through the tunnel or runs back through the tunnel. But the problem is that no matter which way he goes, if he runs back this way, the train will arrive at this same meeting point, the entrance of the tunnel, at the same time. And if he runs ahead at this point, the train will also catch up him at exact that point. That is very interesting. So now we want to know the speed of the man. We do know the train of the man. So, okay, quite a bit information. How do we attack this problem? Of course, this is just a typical speed-related problem. first of all, you should trust that you will have enough information to solve this problem. Meaning that no matter how you choose your variables, you should be able to get just enough number of equations to solve that. Because you are asked to get the speed of man, so why don't we set up that? Where's my mouse cursor? Oh, there we go. Oops. Okay, here. Okay, so we know the train speed is 60 miles per hour. Why don't we say the man's speed is just s? Okay. So now we face a choice. How do we choose some other variable? Apparently, the single variable is not enough because we have quite some just kind of um, actual information here, a lot of relationships. So apparently, a single variable is not going to do it. We have to choose some other variables. This is where it comes to a decision. How do we choose some other variables? So we take a look at information what we have. This is interesting. We did not know anything about the actual distance, like miles, meters, kilometers. We don't know anything. But we do know the man, when he heard the train coming, he was at 2/5 of the tunnel's length. So that means that our distance is actually measured in terms of a fraction of the total length of the tunnel, right? So that's really interesting because we don't know the distance here. It could be 500 yards, 1 kilometer, whatever. But it seems that that's not quite relevant because we know this is 2/5, and this is must be 3/5, and that is in terms of the total length of the tunnel, meaning that we just consider the total length of the tunnel is just 1, right? So we are interested because this is the distance that we want to know. This should be the variable we choose, but how do we choose the unit? Like a kilometers, miles? Probably that's a very bad idea because the distance we already learned is actually a fraction in terms of total length of a tunnel. So we should stay consistent with that. So why don't we choose this distance between the train and the entry point of the tunnel as an x, but this x is also in terms of the total length of the tunnel. Essentially, this is the ratio between this distance and the length of the tunnel. In other words, we are just mimicking the fractions here. So this is actually a fraction number with the tunnel length as the base as 1. That should be our properly chosen the distance. Okay, with that in mind, we need to now find our equations. And they, they come fairly straightforward because the relationship is really in this sentence whether the guy runs ahead or runs back, he will reach the end of the tunnel at the same time as the train. So first of all, this means that both the train and man would spend exact same travel time. And we know how to find the travel time if we know the speed and the distance. And not just once, but twice, because toward each end. So that means that we would have two equations for both because we have two ends. So that really gives us two equations. And at this point, you should feel very comfortable because you only have two variables. One is the man speed, one is the distance between the train and tunnel's entry point. You have two variables, you have two equations, then everything can be solved. So let's just do that. Let's take a look at the first and the beginning of the entry point. If the man runs back, so he how much time he would spend? He would spend the distance 2/5. This is the distance he needs to travel divided by his speed, right? We know that the time is distance divided by speed. His speed, let's just say we assume is s. This would be the time he needs to run back to the entry point. And that would be the same as how much time the train would take to reach this point. And we know this distance x is traveled by the train, and the train speed is already given to you is 60. So we first write down this equation, right? This is very straightforward. This is just like um, similar to our last problem when Hero Nash and Sally runs toward each other in opposite direction. They have to meet problem. And now the second equation will come in this direction. We know now essentially the train is chasing the man, and that's similar to the earlier circular track problem. One guy is chasing the other um, um, guy, so from behind. So in this case, um, still the same kind of relationship. The distance traveled by the man now is 3/5 and same speed. But the train has to travel x plus one full length of the tunnel, so that's plus one because everything is in terms of tunnel's length. So this time when the train is chasing the man, the distance traveled by train would be x plus one, but the speed is still 60. So we have another relationship like this. All right. So now you should feel very confident. You have two variables, two equations, and you need to solve them. And in this particular, you observe something funny because the equations are quite of similar. On left hand side, they have one is 2/5 over s, one is 3/5 over s. That's really proportional, right? The second one is just kind of 50% bigger than the first one because they have the same denominator. The numerator, one is 2/5, one is 3/5. So essentially, if you think about it, how do you solve this equation quickly? If you multiply 3 over 2 or 1.5 on both ends for the first equation, then you will get the same quantity on the left hand side for both equations, right? Because this is 2/5, this is 3/5. So if you times 1.5, 3 over 2, this guy will be equal to this guy. And that means that on the right hand side, they will also match each other. So that is the idea. So that's why don't we just do that? This way you can see that we essentially cancel out the s part because on the right hand side, there's no s. But essentially you use this, you cancel the one equation, but you also kill one variable. And this is just particularly just nice for this particular problem. In general, you cannot do that. So why don't we just do that? So x times over 60 times 3 over 2 must be equal to x plus 1 over 60. Okay, so the remaining is fairly straightforward, so we are not going to solve this. This is a very easy to solve equation. But the analysis part is more important, how to read the problem. If you feel that the problem is kind of complicated, don't panic. Just draw a nice, just picture, diagram, whatever, then find out the relationship and have faith that you will have enough relationship just to solve the variables. So once you reach here, everything should be straightforward. Okay, that's this problem. Okay, so this problem. Well, this is a problem. It's generally just kind of we are not going to solve that because it is asking a question, but both problems of the same nature. That's why we combine them together. Let's go back to an earlier problem. So Marco starts hiking on a path at noon. So Ned stops at 8 p.m. in the night. He rests until noon the following day, and then starts hiking back towards his original starting point along the same path. He gets back to the starting point in 8 hours. So you can see very interesting. He the first day he starts at noon and stops at 8 p.m. Spend 8 hours in total. Then on the second day, he again started at noon, but goes back, and then he again spent uh, to the starting point 8 hours after he starts walking. So in both days, he spent the same amount of time, 8 hours, and of course, just back and forth, he traveled the same amount of distance. He does not necessarily walk at a constant rate either day, meaning that he just did not have a steady pace. Sometimes he walk very slow, could sometimes could like even walk very fast. But explain why there must be a point on the past that Marco visited at the exact same time on both days. So this is interesting. Sounds like how this is not typical word problem, right? It's a logical problem, but you should have a very good intuitive understanding of the nature of the problem. You are asked to explain why there must be a point on the past that Marco visited at the same time on both days. So if this is a distance, the first day the guy goes from here to here, the second day goes back from here to here. Recall that in both days he started at the same time, noon, 12 o'clock, and reached the destination at 8 o'clock in the evening. So start at the same time, stop at the same time, and travel through the same distance. That's kind of very special. But we will need to argue why somewhere, somehow along this path, there's a point in this direction. He passed this point at a certain time, but on his way back, he also passed this point at the exact same time. Why is that? So this sounds kind of just how do we do this? Well, you just need a little bit of creativity. You just imagine that on the second time, it's just a different person rather than himself travel along that direction. Then you time shift that back just trip to the first day, right? Just imagine that almost like say um, he copied himself from the second day to the first day. Now in that case, it's just like there are two people running against each other. Essentially, you time shifted the second travel to the first day, 24 hours earlier. Everything remained the same. So if you think about that way, then that means that on the first day, there are two people traveled against each other. They both start at 12 o'clock. One goes this direction, one goes the opposite direction. They start at the same time, going toward each other. They must somehow meet, right? There's no other way. They cannot escape each other. They go toward each other. They start at the same time. Um, Average speed the same. So they will have to, no matter how they travel, they can walk at all different speed at all time, but they somehow still need to meet, crossing each other along this path. We don't care where exactly that location is. We don't care about the exact time they will meet at that point. All we need to know is there is a point they will inevitably run into each other, and that explains why there is a point on this route, say somewhere, this guy, Marco, first day, he passed this point at a certain time. And on his way back the second day, he again passed this point, but this time this direction also at the same time. Does that make sense? You just imagine very artificially, he essentially time shift his own travel from the first day, from the second day to the first day. And there's a kind of just a mini me version of Marco or his just a twin brother doing that trip. So the two guy, hypothetically, imaginarily, the two guy will run into each other. So that explains the first problem. For the second problem, this time essentially still the same, but the setup is different. Suppose Marco begins walking back toward his original starting point at noon the following day, but his return trip only takes 4 hours. Does that really matter? Must there still be a point on the path that Marco visited at exactly the same time on both days? Using the exactly same imagination, now we copy or time shifted his second day travel onto the first day. Let's just say on the first day, Marco started at noon going toward this direction. That's why I call this. His twin brother going in this direction, but traveling at a much faster pace. So the twin brother will only take 4 hours from the destination go back to the original starting point. Marco still would need 8 hours. Does that really matter? It doesn't. They still have to meet each other. Even the guys taking the car maybe 20 minutes to get back to the destination, they still need to meet because they travel toward each other on this path. There's no way they can just going across each other with ever meeting at a point. So it doesn't matter that 4 hours or 8 hours, as long as they travel against each other, there must be a point where they meet. And by meeting, it means that at the same time because they both start as new. Okay, so that really explains why in this case there's still a point on that path where Marco visited at the exact same time on both days. Later, you can take a look of the official solution. It just describes this idea in a slightly different visual way. The standard answer will draw a diagram with some just like a coordinate system, but with different setup. Essentially, the same thing as we just talked about. So take a look at the solution later. All right. So now let's do a different problem. This is number 6. Okay. This problem is very straightforward. I believe we did something similar last time, but it doesn't hurt to redo it again. Similar, not exactly the same. Of course, it won't be exactly the same. So the difference of the squares of two distinct positive numbers is equal to twice the square of the distance. At this time, you can almost immediately start writing down your equations and so on. Because a problem like this, it's very specific. The question already coming up immediately, right? So, but let's just still continue to read the problem. You are very tempted to start writing down your equations at this time, but it's generally a bad idea. Why don't we read the whole problem before we do that? So what is the ratio of the smaller integer to the larger? Express your answer as a common fractions. Okay, so we just need to know the ratio. That's why we need to refrain from start doing the problem. First, we need to know what we want to solve. We are not asked to get the exact values of those two numbers. We just need to know the ratio of the smaller to the larger. So that becomes easier. So let's just say those two numbers are x and y. And without loss of generality, we assume x is the smaller number. In general, there must be one smaller or equal to each other. This is always the case because the relationship, this is the axiom between the two numbers, and this they are real numbers. There must be one that smaller or at most equal to each other. So without the loss that generality, we assume x is the smaller one. The worst case is they are equal to each other, but that's fine. So what does the first statement tell you? The difference of the squares of the two distinct numbers. So difference of squares, that means the y squares minus, because we're already assuming y is the larger one. So that's the difference between squares is equal to twice the square of that difference. So this is equal to twice the square of that difference. The difference is y minus x. The square is taking square and then times 2. But this actually exhausts our relationship. That's the only thing we know from this problem, right? Yes, the difference of the squares of the two numbers is equal to twice the square of the difference. So this equation exhausts all the information available to us. Apparently, there are no solution or unique solution to this problem because we only have one equation, but we have two variables. That's exactly why you need to read the whole problem. But you are not supposed to solve x and y. You only need to know x over y, right? So why don't we take a closer look at this? What is exactly this relationship? Wait a second. This guy looks familiar, right? Okay, first of all, we can do a quick factorization. This is y plus x and y minus x equals 2y minus x squared. But here comes the question, can x be equal to y? Because we, at this point, we are very tempted to do this. Okay, then read the problem carefully. There are two distinct positive numbers. They cannot be equal to each other. So our general assumption should have been a little bit more rigorous if we notice this already, but it's not too just kind of bad if we did not pay attention to this. We generally you add less than or equal to, which is fine, but you do need to keep in mind, check whether y can be equal to x. So they're not equal to each other, so x must be strictly less than y. That allows us to cancel out one of this. Okay, so now we got a relationship y plus x equals to 2y minus x. But still, we cannot solve x and y, but all we need is the x-y relationship, x over y. Can we do that? If you have at least a reasonable amount of good algebraic sets, you can see that this is kind of just all the linear equations. You can easily manipulate that. So y plus x equals 2y minus 2x. All you need is to put y on one side and x on the other side. So you move 2x to the left, that becomes 3x on the left, and then you move the other y to the right, you get this relationship very clearly, clear and easy. So therefore, x over y is just 1/3. Okay, so no big deal. It's just this kind of problem you should have confidence. You have enough information to solve the thing that you want to solve. Otherwise, the problem is not legit. With that confidence and faith, all you need is to correctly identify the relationship and do what you need to do to get to the result. Okay? If you think that this is too complicated to solve, then don't panic. At least something is going on. The worst you can do at this point is to expand this, to write this down into x squared plus y squared minus 2xy. And that will give you a big headache because eventually you still can figure out, you can combine them, then redo the factorization, but you should recognize that you don't have to go through that long winding path. At the very beginning, you can factorize y squared minus x squared. Of course, this is very easy, but this is a good test of your fundamental skills. If you don't recognize that you can do factorization on the difference of square, I'm sorry, my friend, you probably won't go very far in math competition. All right. So let's do the next problem. Okay. This problem. So we have a formula for the energy given off by a spherical star, like a sun, whatever. Every star is a sphere, right? So such as sun. So we know this formula is sigma, this Greek letter sigma times a times t to the fourth power, where sigma is a constant. So we know we don't worry about that too much. It's a constant. It's just a number. A is the surface area of the star, and T is its temperature. Okay, whatever physics gave us such a formula. This spherical star JZ114 has 10 times the radius as our sun, but its temperature is only 1/2 of the sun. So at this point, you should feel very confident. This is really just about a ratio problem. Not surprising to see the question, what is the ratio of the energy JZ114 gives off to the energy of sun? So you really just need to compare two, let's call this JZ114 over our sun, right? ST sun. Okay, you want to compare those two. That's exactly what the question is about, the ratio of the energy. So you just need to compute this. So let's get some low-hanging fruit first. We have sigma is a constant. We don't care. We can cancel that. We know Tj, this star's temperature is just 1/2 of our sun's temperature. So this is really just, we can get this is because we take to the fourth power. This guy is nothing but 1/2 to the fourth power, and the sun's temperature to the fourth power. So then once again, we can cancel this out. So this really is just the area of this star, surface area over the area of sun, times 1/16, right? This is the ratio you want to compute. Now, how do we know this? Well, you have to know a very fundamental thing. What is the ratio of a geometric matrix between two similar things? What do we mean by that? Let's consider this is a sphere, right? But we are talking about surface area. What is area? Area is a two-dimensional quantity. And for geometrical similar things, there is a very important relationship in terms of proportion. Let's consider two triangles. We have two similar triangles. What do we mean by similar? Well, similar can be rigorously defined, but because this is not a rigorous geometry class, we will just not try to give you a full rigorous definition of similar, but you do know that in the case of like a triangle, it could be, say, you can move this triangle to here, and you know this is a parallel, right? This line and this line is triangle. So the two triangles are similar. When two geometric figures are similar, there's a similarity ratio, and that's usually defined through a one-dimensional quantity. What do we mean by that? That's, in this specific case, is the ratio between this length. Let's just say this is A, B, C, and this is D, E. This ratio is really DE over AC. Okay? So this is their similarity, there's a ratio. And it's very important to understand this ratio is between two one-dimensional quantity. What do we mean by that? This is a line segment, right? A line segment is a one-dimensional quantity. Let's call this as R, representing a ratio. So this is the similarity ratio between those similar geometric figures. Now, if I have to ask you what is ratio between the two areas, so this is the area of the smaller triangle, and the bigger triangle area is represented by the yellow highlighted area. What is the ratio between the two areas? It's very important to understand if we say the area of triangle BDC, which is a smaller one, over the area of BAC, of BDE, I'm sorry. So smaller is BDE, and the bigger one is BAC. What is the ratio between the two areas? It must be square of R squared. This can be proven, but in general, you just need to understand because the area is a two-dimensional quantity, and when you have two similar figures, any two-dimensional quantity corresponding two-dimensional quantity, the ratio would be square of the first dimensional ratio. So that can be further extended into three-dimensional quantities. So let's just say you have two similar 3D figures, and the one-dimensional ratio in terms of similarity is R. Then the two figures' volumes ratio has to be R cubed because that's three-dimensional. It's not that difficult to understand this. Let's just consider the simplest case of a geometric 3D figure. This would be rectangular prism. So what is a three-dimensional quantity? Could be volume, right? So in this case, it will be the length times the W times the width times the height. Because volume is a three-dimensional quantity, that is generally the product of three first-dimensional quantity. And we know if there's a corresponding similar one, then because each dimension in terms of L and W as H, those two similar ones, L is in that proportion, height is also in that proportion, W is also in that proportion, you have to type a multiply R 3 times in order to get the ratio between the volume between the two. That's why for three-dimensional quantity like a volume, the volumes ratio between the two would be R cubed because that came from this fact. Of course, we are trying to give you a very intuitive understanding. This can be rigorously proven. So back to our question, if you have two stars, this J, Z, R, C, we have a sphere, right? And this is our sun. We know their radius, remember this is not circle, this is a sphere. Their radius ratio, radius is the first dimensional quantity. The ratio between their radii is 10. What is the volumes ratio between the two sphere or two stars? Must be 10 to the cube because volume is a 3D quantity. And the first dimensional ratio is 10, then 3D quantities ratio must be 10 to the third power. But that's not what this problem is about. This problem only talks about surface areas ratio. Well, whatever area you're talking about, surface area, that's a two-dimensional quantity. Therefore, the surface area ratio must be 10 to the second power, 10 square. That means that AJ is the surface area of this JZ114 over the area of our sun. This one must be 100, which equals to 10 to the second power. So the answer is really 100 times 1 over 16. Of course, you can simplify this. This will be 25 over 4. Okay, so we spend this much time really just to talk about a very important um, geometrical property. Of course, this can be further studied, but it's not that difficult to intuitively understand why. And this actually is super important in AMC and Mathcounts because they frequently give you problems of this nature. This is called proportional arguments, especially in terms of the area, the volume, and so on. Just try to understand this intuitively. When you have two similar geometric figures, in terms of various kind of proportion problem, you think about a first dimension similarity ratio. Always remember that's the first dimension. Like two similar triangles, if they have the height, altitude, that's a first dimensional quantity. It doesn't matter how you choose that one, they're all the same because all the first dimensional quantities are in that proportion or ratio. So now, if you talk about any corresponding two-dimensional quantity like area, the ratio would be that first dimensional ratio take a square. And if you talk about 3D quantity like a volume, then you take the cube. Okay, that's a very important thing to understand, and you can use that very easily in various such problems. Okay, we run out of time, so we'll stop here. So this week we have a lot of word problems. We also study some similarity and proportional argument, and hopefully you had a great week. I will see you next time. All right, bye everyone.